Welcome to lesson 12.1, Arithmetic Sequences. Our essential question is, what are algebraic ways to define an arithmetic sequence? Back in Algebra 1, you began learning about sequences, and if you recall, that an arithmetic sequence is a pattern of numbers that increase or decrease at a constant amount. It means we're adding the same amount. So if we start with the number 2, we add 2 to get 4, add 2 to get 6, add 2 to get 8, and so forth. We're adding the same amount every time. And we have a name for that. We call it the common difference. Just a few things about sequences in general. We call this first number the first term, second term, third term, fourth term, and these 3 dots just means it goes on forever. Now we usually use the word term. That's what you'll hear me use. But someone might also use, say, the first element, the second element, or the first member, the second element. They all mean the same thing. Okay, it's the numbers in the sequence. So let's take a look at another sequence down here that I have. I have 5, 10, 15, 20, 25, 30. Now you can probably right off the bat figure out what the common difference on that one. But just to remind you about how to find the common difference, you take the second number, in this case 10, subtract the first number. That gives me 5. Okay, so that means we're adding 5 each time. I could also take 15 and subtract the one before it, which is 10, and I get 5. And sometimes you need to check all of these to make sure that you're adding the same amount each time. And it doesn't start out adding 5, adding 5, adding 5, and all of a sudden switch to adding 10, adding 12. So it's really important that you check each interval and make sure that you're adding the same amount. You can also add negative numbers, which we might say you're subtracting the same amount each time. Same thing, you're just adding a negative number each time. Sequences can be represented as functions, and we're going to look at several different kinds of sequences. Today's are arithmetic sequences, tomorrow geometric sequences, and they can all be represented as functions. And it's kind of sometimes difficult to see when you're given a sequence like 5, 10, 15, 20, 25, 30. What is the input? What is the output? So I just kind of want to remind you that for a sequence, these numbers, 5, 10, 15, 20, that is our output. So if I was going to make a table, I would have the sequence as my output. So we might say, okay, what's the input then? So the input, we're going to use n for sequences, no longer x, you're going to see the letter n. Still just a different variable. Our input is the position number. So for instance, the 5, that is in the first position. 10 is in the second position. Third, fourth, fifth, and so on. And it would continue. You're going to see in the textbook the output, the sequence, in function notation using f of n. I'm going to detour from that, and I want to show you, which typically all other textbooks and all your higher math classes, they're going to use this other notation. It's going to use a sub n. Okay, so the a standing for a sequence, okay, and this subscript, forgot it there for a minute, so the subscript n, okay, is your input. So if we were looking for the fourth term, okay, so the fourth term would be written a, my pencil here, a sub 4. That would stand for the fourth term. Okay, so something like a sub 2, that would mean the second term. So we're going to start using this notation so that you become more familiar with it. All right, hopefully you have your book open to page 585. At the top of the page is a large paragraph that goes through the definitions of a sequence, arithmetic sequence, and it also has a review of the word explicit rule and recursive rule. The one we're interested in is the explicit rule. It's just what we're used to. It's like y equals mx plus b. It's writing the equation with an input and an output. In the middle of that page, your book goes into all this language about how to write these equations. I'm going to simplify all that for you. You probably want to record this either in your notes or your book somewhere. This is the information that, yes, you do have to memorize this. All right, some functions or sequences, typically, they all start with the n equals 1, right? So if you think of a sequence, you've got the first position, second position, and so forth. Typically, we don't talk about the 0th position, but once in a while, you do have some sequences and you have to be told this, where n equals 0, that you're starting at 0. Okay, so that is something you'd have to be told, most likely in a table or on a graph. You would say, oh, n equals 0. So your function or your rule is a sub n. So this is just like y. So if you want to think about it, we're not going to use y. Okay, but that's the same thing as y equals a sub 0. Okay, that is the sequence number, okay, when n equals 0, plus your common difference times n. So when you write this equation, a rule, let me go back to a rule, these are the numbers you're going to be filling in. You're going to be filling in a sub 0, which is the very first number in the sequence when n equals 0. And you're going to be filling in the common difference. Okay, the a sub n is what we're used to calling y. N, okay, is our variable. Now what if the sequence starts when n equals 1, which is much more common? Okay, in that case, we're not going to start with a sub 0. We're going to start with a sub 1. Okay, a sub 1 is the first number in the sequence. D is our common difference. Now in parentheses, you're going to have n minus 1. Okay, let's think about this. Recall y equals mx plus b. Yeah, these are linear equations that we're working with here, arithmetic sequences. So remember what b, the y-intercept, was. That was your starting point when x equals 0. Well, look how that corresponds to that starting number when n equals 0. And your common difference, okay, is your slope. It's your rate of change. And we've just changed the variables from an x to an n and a y to an a sub n. So notice that when we go up 1, we change n equals 1. So we change the starting one to when n equals 1. We have to change our n just slightly, and we have to rewrite that as n minus 1. So these are two equations that you need to memorize and become familiar with. All right, so if you'll turn over to page 586 in your book, we're going to look at example B here and how this works. So we're going to be given a sequence. In this case, it's in a table. If you look at that table, let's look at n. N is starting at 1. Okay, that helps us out a lot. So remember, these are the position numbers, 1, 2, 3, 4, 5, 6. Here is our sequence. And we're asked to write an explicit rule if this is arithmetic. So the first thing we have to check is this actually arithmetic? So we're going to take 25 and subtract 29. So 25 minus 29 is negative 4. And then we're going to take 21 and subtract 25. That's negative 4. So let's keep checking it. 17 minus 21 is negative 4. 13 minus 17 is negative 4. Looks like we're going to have a sequence here. And 9 minus 13 is negative 4. So the difference is all the same. So therefore, this is an arithmetic sequence. Now the initial term of A, of the sequence, there it is. There's the very first term in the sequence, is 29. Its position number is 1. Okay, so we talked about that n is starting at 1. And we already said the common difference is negative 4. And that's all the information we need to write the explicit rule. So down here below, I have our formula. So let's just simply substitute in. So I'm going to leave it a sub n, that's kind of like my y, equals the first term in the sequence. So that first term in the sequence was 29, plus our common difference is negative 4, So negative 4 parentheses n minus 1. So let me write that again. We probably would more commonly write that as 29 minus 4 parenthesis n minus 1. That is our explicit rule. Now you might be thinking, do I need to distribute this? Do I need to simplify? No. This is the typical form that you'll find a sequence in, so you can leave it in that form. All right, below that example in your book is a your turn number 3. We're going to do this one together here. And it says use the table to write an explicit and a recursive. We're not going to do the recursive rule for the sequence. So first of all, let's see if this really is. So I'm going to take this negative 2 minus a negative 7. That gives me a positive 5. So here I'm adding 5. Let's see here. Do I add 5? Yeah, negative 2 plus 5 is 3. Here, do I add 5? Yep. Add 5? Yes. Add 5? Yes. Okay, so all those are adding a 5. So my common difference is a positive 5. I also have my first term, which is negative 7, and n is equal to 0. So this is one of those cases where we're told n is equal to 0. So we can jump straight to writing our rule. A sub n equals, if you remember correctly, it's the very first number in the sequence, which is negative 7, plus the common difference, which is 5, times n. So there is our explicit rule. Now to double check this to make sure you wrote it right, let's take a number up here, right here. Let's take 4. And let's plug in 4 here. 5 times 4 is 20. Minus 7 is 13. Is that what we want to get out? Yes. So we most likely have the right equation. Now the reason we write this equation is that we can find any term in the sequence then. So what if I want to find the 65th term in the sequence? Well, I'm definitely not going to write the sequence out until I get to the 65th term. As mathematicians, we want to compute. So I'm going to use so this simply means n, let me get my pen here, is now going to be 65. So using my equation, I can just put in negative 7 plus 5 times 65. So we find out that the 65th term is 318. So arithmetic sequences should be a review for you from Algebra 1. Most of it is terminology you need to be familiar with, and those 2 formulas for the explicit rules. You do need to memorize them, but keep in mind they're linear equations.